All right, so this is lecture 18 and this is video 1, machine learning from data. And in this video, we are going to discuss something that's known as radial basis functions, or you might have seen RBFs. This is what we're going to discuss in this video, and we'll begin by talking about non-parametric RBF and then move to the parametric one. And finally, the K-RBF network. So all of that in today's lecture. Let's quickly recap what we did last time. And in fact, this relates really well to today's lecture as well. Last time we dealt with memory and computational issues with the nearest neighbor algorithm, but then we figured some really effective methodologies of dealing with these two issues. For example, we can reduce the amount of data, and then going after the training set consistent technique where we could get rid of the data and still have the correct classification or the original classification. That was the first thing we looked at. And then more importantly, we looked at the branch and bound for finding the nearest neighbor to quickly find or efficiently find the nearest neighbor, how to do that. And we saw that in many situations, we can get structured data, and that's really good for us. So that's like a way to quickly find the nearest neighbor. And if the data is well structured, we can save a lot of searching, we can save a lot on searching cost if it's like well separated and in clusters. All right, and then finally we ended with the Lloyd's algorithm for finding good clusters, right? How to find clusters was the question, because if there are clusters in the data, we need to find them. And so Lloyd's algorithm helped us do that. So like all in all, we talked about data condensation, and if you remember, the CNN, and finally improving on the nearest neighbor search. All right, so having talked about having improved on memory and computational issues, we ended the lecture with one question, and then I'm like repeating that again. So in K nearest neighbors, when we were trying to find neighbor for a test point X, and like these, let's say these are the neighbors that I'm looking in. And let's say there was like right outside this like range of K nearest neighbors, there is another class. And so because we are just like focusing on K number, some input parameter K essentially, then why aren't we like taking care of these points that are not included in those K nearest neighbors, right? So how about like if we use all the data to compute G of X, right? And then again, we might like the intuition is that if we are doing that, then we are definitely like creating computational issues and memory issues for us, right? But that's fine. How about the actual misclassification issue, right? If you're not really solving the problem, then the whole point of having a model that classifies a point is defeated, right? So here we have something that's known as the radial basis functions, or RBF. What they do is they find some kind of a middle path in the sense that they use all data, but then this data is weighted in the sense that you can use the entire data that you have, but then there is this relevance of the points that are nearer to your test point versus the ones that are further away. And that makes sense intuitively, right? So it's allowing you that you can use all the data by weighing in the relevance of some points as compared to the others, right? So instead of using some data, we'll use all of the data to predict for a test point. Okay. So that's the general idea of radial basis functions, or RBFs. Now let's look at, let's actually try to understand the non-parametric radial basis function in one dimension. So let me write it down. Non-parametric RBFs. And what are these? And you will see these are like intuitively very similar to the K nearest neighbor. In fact, they can be derived from the K nearest neighbor themselves. So here we are looking at non-parametric radial basis function. Everything we're looking at, like especially when we are observing things pictorially, it's one dimension, but everything applies to D dimension. So it can be generalized to D dimension. And also we'll begin with the lens of regression, but then eventually we'll close with seeing like how this translates to classification or even logistic regression. All right, so if you remember, for the K nearest neighbor, my G of X, the hypothesis was 1 over K, and I is from 1 up to this big K, the average of yi, and this square bracket, just to remind you, if we have like ordered points, for example, the closest point has like 1 and then 2 and then so on. So that's why like the ith square bracket, if you just like don't remember from the previous ones. Or like another way of writing it, we can also say that like if this 1 over k is like the weights are uniform. So if the weights are uniform, we can take this like 1 over k inside, and that would be like a weighted sum. So we can extend this to something called, like, we are trying to move towards the weighted average, right, instead of the average. And so we can extend this idea a little bit, and let me show you first how we can rewrite this here. So let's say I have 1 over k and then yi. All right, so this is all good. As I said, extending it to something that's known as the radial basis function, where I'll use all the data to classify this x. And let's say instead of like these uniform weights that I had here, I have weights that are different depending on like where the point lies. So what that means? That means is that the nearer points get more weightage than the farther ones. So radial basis function is the weighted average of the y values of all the data. Or like, let me write it mathematically. So radial basis function, what would be the g of x, right? That's what we are interested in. So the g of x is going to be the sum of n equals, let's say, n points, right? And then we are talking about the weighted sums. So let me first denote this alpha n of x. And what does this mean? This means that this alpha is the weight, right? And it depends on the test point and also on the rest of the data, that's n, right? So definitely depends on x and on n. So it depends on both, because based on that, like where the other points are, I'm going to decide the weight, right? Where that nth point is basically, and what is its relationship with the test point x. So both are going to determine this alpha n of x. So that's my radial basis function. So like all I'm trying to do is to sum up these weights for every n, right? For like relative to x. So that's what the final hypothesis is going to be. Now, these weights, they do not necessarily add up to 1. So this wouldn't like necessarily add to 1. And so in order to do that, we'll just apply the good old normalization technique. So in addition to this, we can also say that g of x with the normalization consideration is going to be n is from 1 up to n. And this is going to be whatever it was divided by the normalized weights, and I'm using m for the index, times y of n, right? So this is like all the data. All right, and so this is normalized to 1. Okay, so this here, this entire, or like more specifically, this like second equation, oops, should include that. This second equation here is the non-parametric radial basis function. That's all that is to the radial basis function. Get all the data and then get weights of every point relative to my x, right? And then normalize that, and that's it, I'm done. Now the question arises, how do we pick these alphas? How do we get these alphas? I just like said it should be weighted, and okay, the intuition is that the point farther away from x has a smaller weight versus the one that's closer. All of that is fine, but we need some way to do that, right? We need a more mathematical sort of technique to pick those weights. So let's see how we can do that. And again, I'm showing you one example, but you can, like, just by looking at this example, you'll be able to figure out that how weights are usually picked. So let's assume that this is my x, this is my test point, and this is some x of n, right? And so I have to determine that alpha of n for this x of n, that like the impact of that on x, right? And one way of doing that, and also imagine like your data is all spread across the space. And so there is this generic point x of n. It's no special point, right? It's there in your data. I'm just like looking at this one. Now I want to pick a weight that xn has, right? And its impact on x.
and it is like at some distance from my x, right? And I have to figure out a way to kind of calculate its weight. And then also I should have some way of calculating the weights that are in between this distance, and also the weights of the points that are away from it. So I can come up with some function that kind of encompasses that kind of a behavior. So what I come up with is a bump kind of a function. So a very generic way of calling this kind of a function is a bump, right? So this kind of function, and we usually call it phi, and this function is known as the kernel. You must have heard this name many times, and you can tell that the bump is decreasing on this side, right? So this is decreasing. It's also decreasing on this side. So basically this point here, obviously, this is the point on which like I'm interested in finding the neighbors, and so I need to get the weights of the rest of the points, right? And so if you look at this thing here where it touches the curve, that exact thing is going to be my alpha n of x. Okay, so basically what have I done? I have defined a function using which I can come up with my weights. So therefore, alpha n x is, and this could be like any function phi that has something here, right? And depending on our knowledge of how we were trying to determine the weights, we can say here that like the weight of data point xn at test point x is like some function of the difference between these, right? And then it depends on like what that function is going to be. For example, in this case, it's like a very naive way of kind of expressing this. But yes, this is a valid function. This kernel is a valid function. And so it can characterize this kind of a behavior, right? And so we realize here that data may have some intrinsic distance measure as well, in addition to whatever we saw. What I mean by that is like it depends on what problem you're working on, and so you'll have some kind of units you're working with, right? And so based on that units, your data, the magnitude of the values there can be big or small, right? And sometimes they become incomparable. For example, so here we are measuring some distance, and we have to be extra careful when we are measuring distance, because then units might come into picture and they can just like blur the real essence of this distance. So for that, we need like some kind of a scale parameter to kind of deal with that. And so we come up with something that's known as like a scale parameter, as I said. So R is a scale parameter to kind of keep any kind of intrinsic distance in control. And so finally, we come up with the definition of the weights as like alpha n of x is phi, like whatever function, and the distance divided by r. All right, so this R is, as I said, the scale parameter. So that kind of scales if there are any unit level disparities within the data. Now, you can also specify any decreasing function that you want, because you must be wondering like, what is this phi and what should we specify this to be? And so you can specify this to be any decreasing function. For example, and let's look at some examples. Like the first example that I'm looking at is, let's say phi of some s, right? S is a parameter for the function itself, is 1 over 1 plus s squared, right? So this is a decreasing function, and of course, based on this definition of phi, you can calculate the alphas. That's one. S gets bigger, this function is dropping. So this is a decreasing function, and mostly, like, let me write it down. We look for decreasing functions. Decreasing functions, and you know why? Because like this is the max, so this is the point itself. And so every point that's contributing around it has to like decrease. All right. The other one, like some of the popular ones I would talk about, the first one is the window kernel. Two of the popular types, and then obviously you can go back and check if you are interested in more kernels. So one of them is phi s, and this is like 1, 0. It's 1 if mod of s less than some r, and if s is greater than r. You can just tell by looking at this. Let's say this is my test point, and so this is r and r on both sides. And so this is more like a window, right? basically collect all data points within the window and have their weights equal. So everything like within this range is going to be equal, and then the weights like begin to decrease after that, or they are less than this. Maybe like it depends on like how we've set up our problem. Another even more popular one, so this is the first one, the window kernel. The second one is the Gaussian kernel, and I'm very sure you must have heard this one. So the Gaussian kernel is my phi of s is e square 2, and you can tell just by the name, this is what it looks like, kind of an ideal one. And by the way, like it's both sides, they are equal and not like one being more than the other. Let me make it better, but I cannot guarantee that I will be able to make it better. Okay, slightly better. And so this is my x, and you can see the weights drop in either direction, right? And also if we think about it, so like within this like range, you'll have like higher weights, and beyond that, it's like really quickly going down to almost zero. So if you think about it, it's a softer version of the window kernel itself, right? It didn't have like the window kernel didn't have like these soft edges, and so it was just like either be within this or like you're zero outside. But here it's not the case. So it's like a softer version of the window kernel, and this is used a lot throughout. So these are like some of the examples of kernels. Of course, you can go and check more. And so finally, let's like kind of try to summarize what the non-parametric radial basis function is. So my hypotheses, and n is from 1 to n alpha n for x. So now we understand why that is. And then normalized weights, m is from 1 up to m, and then alpha n, where my alpha n of x is some phi of this distance x minus xn over my scale parameter. Okay, we didn't need two brackets, but that's fine. All right, so this is a non-parametric radial basis function for regression, right? We looked at it through the lens of regression. But now, given that like whatever we have done until now, it's pretty easy, I would say, to kind of translate it to classification and logistic regression. So what are we looking for classification? Well, for classification, our goal is to get the sign, right? So instead of getting that sum, I'll get the sign. My g of x is going to be the sign of the sum of that term. That's this alpha n x over the normalized weight, and the rest stays the same. That's the only difference that's there to this. And then comes logistic regression. So how to apply to logistic regression? Now you can tell in logistic regression, we're not exactly looking at the y's or the sum of those, but we are looking at the weighted proportion of y values that are +1 or -1, right? So that's what we do. And so in logistic regression, it's going to be g of x, and instead of like this entire term, let me call it like big X for the time being. You can call it something else, but just like I don't want to repeat the same thing, with an indicator function where yn is +1, right? So just like counting the fraction of those values, that's all. Okay, so of course we can translate it to classification and logistic regression as we just saw. Only thing we need in this case, and why is like we are emphasizing so much on non-parametric, that's because we don't need any parameters except r. And also r is just like based on the data, right? It's not really a parameter, but yeah, of course you can say that's a parameter, but depending on the data, you're just like trying to fine tune, and so there isn't like really a parameter, so that's why it's known as a non-parametric radial basis function. Okay, it definitely inherits a lot of, I would say, properties from the k nearest neighbor, in the sense that we did not require any training. We're using the entire data and just like getting the classification or regression, whatever, getting the results in just one go, right? So we are not really like there isn't like a procedure for training and then testing and so on. All right. So let's quickly look at the comparison of both the algorithms, the nearest neighbor on the top and the non-parametric radial basis function on the bottom. So if you look at the top row, and this is like something that we have looked at like multiple times. So k equals 1,
overfitting, obviously, as expected. Each and every point k equals 1 is trying to overfit. And then k equals 3, well, we have seen that this is like the perfect kind of choice in practice. So practically speaking, it has been like established that k equals 3 is the best choice. And then look at k equals 11. So as k becomes like really huge, you can see it's like, it's nothing but taking the average of all the points. That's all we're doing. And so it's underfitting. Really, it's underfitting. Okay. In non-parametric radial basis functions, you can see all we are doing is we are like somehow changing R, right? So, and this is like, by the way, the experiments were done with the Gaussian kernel, and the first one has a smaller R. So just think of the curve being really narrow. So it's like very close to the k nearest neighbor, and the weights are very close to the test point, and like almost having the same weight. So R is like too small. If R is big, then it's the overfitting region, right? What's happening is R is large, and so my x minus xn over R, that is going to become small, like it's going to be like approximately a constant. And that is something similar to the nearest neighbor for a large k, which is like the case here. And so that's why it's the same case here. All right. So you see that we said that it's a non-parametric radial basis function. However, we see that this R is somehow impacting my final hypothesis, which was quite expected. So how do we choose R? One way is cross-validation, as like is recommended here, of course. And in k, like in the k nearest neighbor, we also came up with this like theoretical sort of relationship between k and n. So can we come up with a similar relationship between R and N? Yes or no? Well, in some ways we can, and let's see what we can do about that here. Let me actually use another slide. So, like for the k nearest neighbor, we said that k equals square root of n is theoretically a good choice for k. And so theoretically speaking, for what value of R can we have this kind of a relationship between n? So one quick example for that is that something like that. So if we want like the square root n neighbors to contribute, right? So for example, this is x and this is R, and x is my test point, R is the scaling parameter, and these are all the neighbors that are contributing to x, let's say, in this space. And let's say this is like a sphere region or something, right? So the volume of this region is proportional to R to the D, right? Whatever the dimensional data. Now, what happens is that the number of data points in this region is like overall is going to be number of data points will be proportional to NRD, right? And so probability of being in this region is like basically from some distribution, this data comes from some distribution. So probability of landing in this region is like this thing times the probability of that. And we want this number, the probability of something times NRD, to be equal to square root of n. So like conceptually speaking, we want something like this to happen, like NRD equals square root of n. This is something that we want, right? So theoretically speaking, this is 1 over square root 2d over n. Okay, so this is like kind of a recommendation, a theoretical recommendation, of course, and R actually in practice depends on the problem that you're looking at, the data that you have. But this is kind of still giving us a good intuition about the relationship between R and N. Now, as like you can say that as N gets large, that means like closer data points, and we have more closer data points and many of them are contributing, right? As R becomes large, that means we have far away data points contributing too much, like the away ones, right? And if R is small, not enough data points contributing. So basically we want R just right, and then all the points contribute. But still this kind of relationship exists and we can always like use it. Again, pointing us to the same direction, just like what we discussed just now. Okay, just to summarize, before we end this video, so some of the highlights of non-parametric RBF are very similar to the KNN. In fact, sometimes it's known as the smooth version of KNN in the sense that like, of course, I'm taking some neighbors, but their weights instead of like taking them exactly. So it's simpler. Again, no training required.
Just like even for this near optimal, remember for the near optimal rule in the k nearest neighbor, we said like when k n tends to 0, that means both k and n are increasing, but k is not increasing as fast as n. So similar kind of logic, similar kind of intuition applies for r as like instead of k. So r versus n, and we can like achieve near optimal. And it's again easy to justify classification to customer. Why? Because it's easily explained. It's an explainable model. You can easily justify why we are using this versus that. And it's also equally like it's applicable to classification, as we just saw, logistic regression, and especially multi-class problems, similar to our nearest neighbor, right? Easily applicable to that. Because if you think about it, it's not really a lot of difference between what we were doing in KNN versus this. It's just like a slight tweaking in terms of the weights that we are doing. That's all that is to this non-parametric RBF. However, as you might have guessed until now, right? And of course, like, there's no training. I think I talked about that already. Um, so, like, you must have guessed by now that this is again computationally demanding, right? Again, I'm using the entire data and I'm doing some kind of calculation using that. So I need to come up with something to kind of address that, just like I did with the nearest neighbor. Of course, like you can always say, let's throw away some data. And so my question is like, can we do something better? Or maybe, yeah, just like, let's throw away the data, but how to do that here? So that's something that we're going to talk about in the next video. So I'll end this video now.